The 20-millisecond failure. The New Glenn second stage experienced a catastrophic underperformance on April 19, 2026, specifically because one of its BE-3U engines failed to reach full thrust during the mission's final orbital insertion burn. While the first-stage booster landing on the Jacqueline ship provided a clean visual for the webcast, the telemetry tells a different story. The Bluebird 7 satellite was left in a decaying 150-kilometer orbit rather than its 460-kilometer target, effectively turning a high-stakes commercial mission into an expensive re-entry experiment. This failure points to a fundamental struggle with managing cryogenic fluids in a vacuum. Next, we look at the specific thermal constraints of the expander cycle engine. The expander cycle trap. The BE-3U is a liquid hydrogen expander cycle engine, a design chosen for its high specific impulse and lack of complex pre-burners. In this architecture, the fuel is used to cool the nozzle, where it picks up heat to drive the turbines before entering the combustion chamber. It is a closed loop that works perfectly in a laboratory, but becomes precarious during an orbital restart. If the nozzle has cooled too much during the coast phase, or if the hydrogen absorbs heat too unevenly, the turbines cannot spin up to the required RPM. This creates a thrust shortfall that the guidance computer can neither predict nor correct. For Blue Origin, this thermal soak period has become a mechanical bottleneck. The propellant settling maneuver meant to fix this had its own issues. The Ullage Gap. In microgravity, propellants float like clouds inside the tanks, away from the intake valves. To fix this, New Glenn uses small thrusters to create a slight forward acceleration, pushing the liquids to the bottom in a process called propellant settling, or ullage. On Flight 3, the telemetry suggests this acceleration was insufficient. Even a small gas bubble in the liquid oxygen line will cause a pump to overspeed and lose suction. This phenomenon, known as cavitation, likely choked the BE-3U's flow rate, preventing it from reaching the necessary delta-V for the Bluebird 7 deployment. These micro-acceleration failures highlight the gap between theoretical engine performance and the messy reality of fluid behavior in a vacuum. Landing is a sideshow. Blue Origin's internal branding frequently emphasizes booster recovery as the metric for success, but in orbital rocketry, the landing is merely an economic optimization. The actual job is payload delivery. By focusing on the booster's return, the public narrative ignores the fact that the upper stage is the only part of the vehicle that actually reaches orbit. If the second stage underperforms, the mission is a zero-sum loss, regardless of how softly the first stage touches down. This disconnect between marketing-driven success and engineering requirements is now under FAA scrutiny. This incident forces a re-evaluation of the entire architecture used for heavy-lift orbital insertion. The Real Implication. The failure of Flight 3 proves that scaling the hydrogen expander cycle for heavy-lift missions introduces nonlinear thermal risks that Blue Origin's current test cadence has not fully solved. While the booster recovery on Jacqueline demonstrates operational proficiency, the BE-3U thrust deficiency undermines the reliability required for the upcoming Kuiper and NSSL manifests. These findings suggest that the industry must stop treating upper-stage restarts as a solved problem and recognize them as the primary mechanical constraint for long-duration missions. For Blue Origin, the 2026 goal of 12 launches is no longer a scheduling question, it is a thermal engineering hurdle. The path back to flight depends entirely on redesigning the nozzle cooling jacket and the ullage thruster duty cycle to prevent another vacuum hard start. Watch the June 12 FAA telemetry release for the final verdict on whether this was a manufacturing defect or a fundamental design flaw. Subscribe for more.